Assalamu alaikum. Welcome, guys. Uh, in our last lecture, where we ended up here, right? We have seen we have seen the relation power spectral density of signal is having a relation or is proportional to the as a spectral density of the pulse. That's we actually have seen in our last class. So in today's class, we will study some new topic. So let's us draw a communication channel. How it happens? Digital communication channel. Digital communication channel. Sorry. Uh, Digital communication channel. Digital communication channel. So what kind of communication channel could be? So channel could be wired, channel could be wireless, right? So anything that carries signal is called channel in general cases, right? Now, for example, this is a channel. Imagine this is a channel. If xt is a signal that is transmitting, so this is a transmitted signal, goes through a channel, and for example, yt is a receive signal. So this is a receive signal. So this is a transmit signal. Yt is a receive signal. Now, in this lecture, we like to know more about this channel. Very popular model of a communication channel is AWGN, which means additive wide Gaussian noise channel. So this is a very popular. So wide Gaussian noise channel. So in this lecture, we will see individually of these properties. How it becomes additive, how it becomes white, how it becomes Gaussian, how it becomes a noise, how it becomes a noise channel. Okay. Now, if I draw a output signal, if we write an output signal yt is the output received signal is xt, the transmitted signal, plus a noise which is added, in the channel while transmission. So because you see this is an addition, that's why we call the additive noise. This additive comes from this one. The nature of this noise is an additive. So noise adds to the signal. So that's why the nature is additive. It's additive nature of a signal. Now we like to know the other two term. So it's a additive wide Gaussian noise. So imagine this is an NT. So NT is a what is this nature? This noise? It's a random, right? Random in nature. Okay. Random in nature. It's also function of t, right? Function of time t. Function of t. Because of this two, it's a random process. This noise, additive noise, we just concluded that this noise is a additive noise. So this additive noise is a random process. That we also concluded from its nature, right? So now we say it's a random process. A popular random process, any among the various random processes, a popular random process is called Gaussian. Gaussian. So we can call it Gaussian random process. Right? So we first decided that this is an additive in nature, so it's additive noise, and it's a random and functioning time. That's why it's a random process, and a very common random process is called Gaussian. So we can call it a Gaussian random process. This noise is a Gaussian random process. So when we call a process is a Gaussian random process, for example, NT. Now this NT is a Gaussian random process. When we call something as a Gaussian random process. So NT is a Gaussian random process if all the orders or sample noise samples are jointly Gaussian. Gaussian. What does we mean it? We mean by it, for example, in T. So it's sample in T1, in T2, in Tk for various. These are the noise samples. Noise samples for every time T1, T2, Tk. If they are jointly Gaussian, then the noise process, the noise samples are jointly Gaussian. The whole noise process is called a Gaussian random process. So it's actually whole will be a Gaussian random process if they are jointly Gaussian. Means the joint distribution is a Gaussian. That's all, right? You know the joint distribution, this term, right? Now Gaussian random process, the another if to condition that they are jointly Gaussian. And so condition 1 and condition 2, what is the condition of these are the condition of the Gaussian random process, right? The noise samples are jointly Gaussian, and it should be a wide sense stationary process. Remember, wide sense stationary. So we already have seen, right, what is a wide sense stationary. When some process is wide sense stationary, if for example our noise process was in T, right? So a NT is wide sense stationary if two condition happens. Condition 1, we discussed this in our previous lecture, right? So this is our lecture 3. I've seen in our previous lecture, right? Let's see. We talked about wide sense stationary process. What was the see, it's a wide sense stationary process. This one, wide sense stationary process. Now, when we discuss about wide sense stationary, we actually discuss two of its property. Yeah, you see, what and in a wide sense stationary process, if any process is wide sense stationary, if there are two conditions, the mean and the autocorrelation, they are time invariant. That's the definition for wide sense stationary, right? So mean, what we say? If it's mean and autocorrelation are time invariant, right? So mean of, so if we find the expected value, we actually find the mean value. So mean is mu for all t. That's, and another one, the autocorrelation. So if we find the expected value of n t and n t plus tau, there is the autocorrelation, right? We can also express it by n, right? Tau for all t and tau. These are the two conditions. So condition 1, condition 2. So condition 1 says its mean are time invariant. So mean, this is the mean, has a mu, like average value mu for all t, time invariant, and autocorrelation. So we find autocorrelation. So any signal, expected value of the signal with its change in instant tau becomes this value for all t and tau. So it's also time invariant system, right? Okay, so we already discussed about the Gaussian. What remains? So we talked about the additive nature. We talked about the Gaussian nature. We talked about the random noise. So white remains. So white. this. So what is a white? So white noise, eh? What is a white noise? If white noise is called to some noise which have a noise noise has very low correlation. Like if I draw a sig noise, like I don't know, like there is no relation with its any instance with the other instance. That is called it's very low correlation. What is the typical signal looks like? If I draw a typical signal, it will be very smooth, right? It will be very smooth signal. But the noise is very erotic. It's very non-periodic, not smooth. Okay. So what is this value then? R in the correlation, the autocorrelation of noise, which we can actually write it as noise t into t plus tau. This value is eta by 2 del tau. So this one gives a correlation. Correlation between nt and nt plus tau. If we draw this this equation, it will be look like this. So this is tau. This is the correlation tau rnn tau. Now if we plot this signal, it would be like this. Nu by 2 del tau. Right? Here, only this instant it has a value. For all other instance, the correlation is 0. So we say correlation is 0 if tau all everywhere correlation is 0, right? Not equal to 0. If tau value is here is 0, eh? If not equal to 0, if everywhere, then this correlation is 0. That's what we are saying. If we plot it, it will be if we plot it, so if we plot it, it will be this. It will have a fixed value. If we plot this, by 2. So this is the power spectral density for power spectral density. Now this power spectral density is how it looks like. It looks like it's a flat. Flat means the power is spread uniformly. So the power is spreaded uniformly all over the frequencies. All over the, so this is F frequency, all over the frequencies. So if any noise is in this power spectrum, so R in T has this value, right? Nu by 2 del tau, the power spectral density of this signal, which is S in like F equal to N by 2, nu by 2. This is the power spectral density, power spectral density, right? Now this power spectral density looks like this, which is a flat. That's why you see the power is spreaded uniformly all over the frequencies. It's like a white signal, like white light. In a white light, the frequencies is, or white light is combination of all the lights, right? From there the name comes. So this is a white noise because this power spectrum density or power is spreaded uniformly all over the frequencies. So we actually define this whiteness also. So we already define all this nature. It's a additive, white, Gaussian, random process. Okay. So we already know that this noise is a, now this noise is actually in our channel, right? If I rewrite the signal again, our signal was xt, right? The noise nt was additive, not only additive. So this noise is a AWGN, additive white Gaussian noise, right? And because this noise is adding in this channel, so you say this noise is added in this channel, this transmission channel. This was a transmitted signal, this is a receive signal, this is a channel, and noise is added in the channel. So this channel is called additive white Gaussian noise channel, AWGN channel. The channel is a kind of AWGN. So that's actually our noise property. So this noise will be added to the channel and we will actually receive a signal. Now we will deal with this receive signal. So you see our chronology, we have in our first two lecture was started with what? Transmitted signal, right? So now we actually seen various characteristics. It's autocorrelation, power spectral, autocorrelation, and power spectral density of the signal. We already know it. Now we actually have seen the channel, actually noise, which actually influences the channel, noise nt. We know its character because that happens in the channel. So we also know the channel properties. The way in a wireless communication system, in wired communication, there is a less chance that some noise will be added, and noise actually adds as a additive. In a wireless channel, these are complex. So random process, lots of stuff actually happens here. So we know a little bit about the channel. Now we will actually talk about the receiver or receive signal or receive system of a digital communication. Okay, so I'll stop here. We'll record a new video for receive signal.